Next up, we're going to explore a really powerful Iceberg feature that a lot of people don't even know exists: metadata tables. We've hinted at these previously. Now it's time to dive in. They let you query the internals of your Iceberg table using plain old SQL, just like you would to query your data. And here they are. Every single Iceberg table comes with these metadata tables that you can query directly. No weird APIs, no admin tools, no ticket to the platform team, just SQL. So you want to see history, data files, partitions, branches, all there, all queryable, just waiting for you, like X-ray vision for your data and metadata. The history table shows every snapshot in chronological order, going back as far as they're recorded. It's your table's timeline. Each snapshot includes its ID, parent snapshot, and lineage status. Is it in the main lineage or off on some other, maybe forgotten branch? Perfect for tracking when changes happened, or maybe just seeing how frequently your table updates. The snapshots table shows you what really happened at each snapshot. You can see the operation type, append, overwrite, delete, along with the manifest list file that tracks all the data files in that snapshot. And you know what? Let's have a closer look at one of these rows, because there's a bunch of JSON in there. It would be good to break that down a little bit. And that's where the real gold is, in that summary field. You've got the number of records added or deleted, number of files created or removed, their sizes, name of the job that made the change. That's a nice little smoking gun, potentially. Even what version of Iceberg was running at the time. And the metadata doesn't lie. You want to track table growth, diagnose performance problems, find out which job went rogue, it's all right here. The files table is where you go when queries are slow and you need to know why. And I'm not going to explain every field here. There are like 20 of them. And honestly, you'll never use most of them. But the key insight here is every single data file shows up here with detailed stats. This is how you catch file problems that kill performance. Like you have a streaming job writing 1,000 tiny 1 megabyte files, you'll find that problem here. Some batch job jumping a 20 gigabyte behemoth that prevents parallelization from working, yep, that's going to be here. The best part is you're not scanning petabytes of data to figure this out. You're just querying this relatively small table. You get to find the culprit and hopefully go fix the pipeline, and in a few minutes your problem can be solved. Let's say we recreate our sales table and configure it to use merge on read and limit each data file to 5 megabytes. Then, with this kind of fun little piece of SQL, we're going to add 5 million records with a few nulls for the region. And hey, it's okay if you want to pause and just look at that query for a minute. It's pretty cool. It's going to just create a bunch of this test data for us and randomly decide which widget is being sold, which region, and whether the region should be null. We'll probably come back to those nulls in a minute, right? When we query the files table, the files metadata table on the sales table, here we just need 2 columns. File size in bytes, that gives us the size of each data file, and we can see that all of them are below the 5 megabyte limit that we just set. That's encouraging. Let's zoom in on this row though. Again, there's some JSON in there. We're going to need to expand that out. The readable metrics column gives us this really nice, human-friendly and machine parsable summary of the metrics for a particular data file. For each column, you get the number of values, the space it takes on disk, and the min and the max values. And check out the region column. There's over 20,000 null values. That doesn't seem right. We didn't expect less. We just generated this and had that little probability in there. But isn't it a great metric for quality checks? I mean, in real life, this would be a problem if we hadn't deliberately inserted those. We would see that and think, oh, that's odd. How are those getting there? And you might need to chase that down. Now let's simulate some random updates and deletes to our sales table. Now, I don't actually have a business story for this. It doesn't really make sense from a business point of view, but bear with me. We're trying to make some things happen in the metadata that we can easily see. So first we'll generate a few thousand random updates and deletes and store them in a table called sales changes. So this query here is just going to make that table called sales changes that's going to command what we do next. And we'll use merge into to apply those operations, that's what I mean by command, into the actual sales table. So it's going to make those updates and deletes actually take place in the sales table. Now let's look at the manifests. And again, I'm not going to show you all the columns. We're just projecting down to a few here. But we have 3 records, which means 3 manifests in the sales table so far. The first manifest had 6 data files to track after we inserted those 5 million records. Second manifest, 1 new data file to track. That was caused by the update part of our merge into command. Third manifest, see that content column is set to 1 over there. That's for the rest of this update that we did. And it's the code for the manifests tracking delete files. This is merge on read, which we selected when we created the table, doing its thing. It's marking rows as deleted without rewriting entire data files. Now, the partitions metadata table. It shows per partition statistics without scanning data files. You got record counts, you got file counts, delete counts for merge on read. This simple query here spots partition skew instantly. When December has 50 million rows and other months only have 5 million, that can wreck query performance. It also shows which partitions have accumulated too many deletes and are maybe ripe for some compaction. The entries metadata table provides file level detail for each operation. What was added, what was deleted. This is really handy when debugging metadata performance issues or understanding the impact of specific write operations. We can get in there in the results and say, well, this path was written, this is how many records were affected, this is the size of the file, all that kind of stuff. There could be outliers here that you might see and say, well, that's interesting, which is kind of the reaction you're going for often when you're debugging and sifting through metadata tables like these. You want to see, okay, what looks a little weird and what other questions could I ask about that? That's often a part of the debugging process, and you can see that kind of thing here. Let's put these tables into practice, solving some real sounding problems. First query, okay, your table grew 500 gigabytes overnight. Yeah, seems bad. What happened? This query right away shows which day had unusual growth, and all of a sudden, Friday is real big, Saturday is real big, Sunday is a little smaller, but you could see kind of a beginning of the holiday season dynamic happening here. So maybe it's not something broken in a pipeline, maybe it's just a real good year, but this gives you some insight. Second, which partitions need maintenance? Instead of guessing, you can get a precise list of partitions that have too many files and might need compaction. And we're going to define that here as more than 100 files per partition, or files that are too small. Average size would be less than 10 megabytes. That would be maybe a problem. So if you look through this query here, we have the case where file count's greater than 100 and average size is less than 10 megabytes. Those are called small files, and we get that nice action column, needs compaction, small files. Nice little analysis of the partitions right there from one query. Third, track your branches and tags with their retention policies. Really could run these queries daily in production. Investigations that took hours now take minutes. You can just spot these things. Say those are liable for cleanup, all from the refs metadata table. So tips for using metadata tables in production, few things. You can build views for queries you run often. Say, health checks, growth trends, partition analysis. That's a handy thing to just kind of have in your tool belt. You can set up alerts when file counts hit thresholds. You can get those file counts easily from metadata tables. You can automate daily health checks. We've seen a few examples of this. Document what you find. This is great for capacity planning. You'll be able to get those results, easily share them. And these queries are, very important point, cheap. They read tiny metadata files, not your actual data. So these are not going to be expensive things to do, and really you should consider making them a part of your daily workflow. Metadata tables give you visibility into what is happening inside Iceberg. Complex debugging turns into simple SQL. In some cases, moderately interesting SQL, but you can do it. That's what you do. This is a database. There's no guessing about table state. Just query the metadata. And based on some of the discoveries we make by looking at table metadata, we might have to do some table maintenance, which we'll look at next.